Okay. So, good afternoon, everybody. I'm just briefly introduce Professor Robert Pontius, professor to be called as Gil, right? So, Professor Pontius is a professor in geography at Clark University. He works with GIS and error assessment and land use, land change science, land use, land cover science. And he will be talking a little bit about the error calculation assessment for us today. And that's it, I think, right? So the floor is yours.
Well, thank you very much, and hello everyone online. You'll be very happy to know that we're having it online today because the room is absolutely filled. There's no more seats remaining, so you're one of the rare people who can have access. Here in Brazil, most people call me Pontius, and that's fine with me. Other people who, from birth, people call me by the first half of my middle name, Gil. If you've seen the literature, I use my full name, Robert Gilmore Pontius Jr. I have been involved in Mathiomas for a while. This is my first year to Brazil, and I hope it will be one of many. But we have funding from the Fulbright program with help from Mathiomas. So let me, on this computer, I don't know more about what might have been disaster. So who am I and why am I here? Well, I was at, in 2011, I published an article with my doctoral student, Marco Milonas, article in International Journal of Remote Sensing entitled Death to Kappa. Have any of you heard of that paper? Okay. One person. Okay, good. I have an important message for you. I have learned that Kappa is extremely popular in Brazil. And so I have a message, and I hope people can actually see this online as I'm looking at the video. Okay. So that was in 2011. That article now has 1,600 citations. And there's been scientists from Mathiomas who saw that paper when Mathiomas started to begin to assess the accuracy of its maps. And there was a particular professor in Porto Alegre, Eliseu Weber, who, after the Mathiomas scientists saw that their accuracies were about 70 or 80%, many Mathiomas scientists felt bad because that sounded low to them somehow. But he had a message from this paper, well, the maps for their particular purposes might be more accurate, depending on what your particular purpose is. So the message of the Death to Kappa paper is not all negative. In fact, some of the messages, your maps might be more accurate than you think they are for your particular purpose. And mathematically, I'll explain why today. So at least that paper got me known by scientists in Mathiomas. And then I met scientists at the American Geophysical Meeting in 2018. And then I became a member of the Scientific Advisory Committee of Mathiomas in 2020. With help of Tazo, we got a grant from the Humanize Institute to start research at Clark University with my students. And we have been meeting almost weekly, every Friday, with scientists from Mathiomas. Julia Shimbo leads Friday meetings where we talk about new mathematical methods to analyze the data. It seems Mathiomas has invested a tremendous effort in creating this time series of data. But now the question is, well, how do we analyze it? You know, to look at it is not really an option. There's too much data. You know, you've got 30-meter pixels for all of Brazil for 36 years for dozens of categories. You can't just look at it visually and immediately see the patterns. And there's so many possible patterns that could exist. It's an art of deciding what to ignore, and as we develop the mathematical techniques. So what my students and I at Clark University are constantly doing are thinking about what are the most important patterns to measure and how to measure those clearly and communicate those clearly and ignore the rest. And at least ignore the details until we first understand the most important patterns. And if we can understand the most important patterns, maybe then we can dive into the details. But mathematically, it's very easy to get immediately dive into the details and then get overwhelmed. So that's what we've been doing. And then my university had the tremendous fortune to hire this year a new professor who is Brazilian, Gustavo Oliveira. Well, there's a Brazilian name for you. And he is a political ecologist, and he has done research on the trade in soybeans between Brazil and China, and has done a lot of work in Bahia and knows many of the agricultural producers. And the United States Space Agency, NASA, is looking to fund research that combines remote sensing, social science in a place where people are adapting to climate change. And so we just last month, we submitted a grant proposal to NASA for $750,000 to study irrigation as a strategy for climate change in Bahia. So if we get that funding, then we will be using this book that I just got today at the university. This is going to be perfect for us. And if we get funding, you'll see lots more of me over the next 3 years. And you can help out with this project. Our budget for this includes money for 2 doctoral students. And so we'll be looking for doctoral students who know GIS, want to study land change, and are fluent in Portuguese. I think I might have come to the right place. And so if you have such students, you can pass on to, I have some literature here about Clark University, our graduate programs in GIS and Earth System Science. And we'll give these to some of the professors here. Julia will have that. So I don't know if I warned you that I came here to sell things. I want your students. I have other ideas to sell also. Let's get into those. And please remind me not to touch that button. I need to touch this one over here. So here are the main points of today's presentation. I will share with you how I developed my philosophy of focusing on the difference as opposed to the agreement when I compare maps. So this approach comes up very often in remote sensing. I will illustrate points with examples from a Venn diagram. How many of you recognize that term, Venn diagram? Okay, it might be, you might not recognize the name Venn, but when you see it, I think you're going to remember it from middle school. All over the world in middle school, you see a Venn diagram in a mathematics class. So the presentation will be recorded. There's lots of mathematical ideas. That's that you need literature. That's why people write things like books, so you can go back and read the ideas. This year, I published my very first book, and I'll give you the link to that. A few years ago, I stopped giving exams to my students, and I said, rather than an exam, I said, you must produce some sort of product that has relevance for people outside this classroom. And so many of my students have produced videos that explain mathematical concepts. And people from all over the world have watched these videos that are at my URL. And for all the procedures, most of the procedures that I'll present today, we have free software. And that's documented in the book. So here's the first part of a Venn diagram. The Venn diagram starts out with the rectangle. The rectangle is the universe in mathematical language, or if you're a geographer, that's the spatial, you can think of that as the spatial extent of the map. Here we have one circle in the Venn diagram. That is one set. And if you have a point in the blue circle, then that's presence of the reference category. And if it's not in blue circle, then that's the absence. I'm presenting this Venn diagram to analyze the mathematics of one class. But our maps have many classes. But I think I better learn how to analyze one class before I try to analyze multiple classes. So if I can analyze one class clearly, then maybe I can just extend that to analyze maps that have many classes. So this is going to focus on one class, and at every place in the map, you either have the presence of that class or the absence of that class. And so the blue is the presence, and I'm calling that, I have the name reference there. You can think, if you believe in truth, you can think of the reference class as the true presence of that particular category. Well, it's blue, so maybe the reference class is water. And that's where water really is, according to the best available information. Okay, so that's why I call it reference rather than truth. The challenge of getting reference information is you can have multiple people look at the exact same image and not agree on what the land cover is there. So that's why I'm saying reference. If you are thrown off by the word reference, just think truth. And then to make a Venn diagram, we have a second circle. And so the red circle would be that same class, but how it's portrayed in a map. And so there's the two circles of the Venn diagram. Now, do you recognize the Venn diagram? Yeah, you remember. See that in elementary school? Okay, a couple of people were paying attention in middle school. Okay, goes way back. Okay, I'm giving this a similar type of workshop all over the world. People remember that Venn diagram, but you might not recognize it because Pontius has a big innovation. I did not like the Venn diagrams in my middle school because they weren't drawn like this. What's my new innovation? I made my circles different sizes. When they showed me in middle school, both circles were both the same size. I'm like, but then my math teacher said, well, they look the same size, but that doesn't mean that you have a mathematical proof that they're the same size. And I'm like, well, why did they draw them the same size? okay? Because they're not necessarily the same size. Okay, so I have them as different sizes. The red one is smaller than the blue one. If your circles are different sizes, then you have quantity disagreement. And that's important to know. If your map, the red circle, is, in this case, it's underestimating the true size. Gosh, you think, if I'm making a map to diagnose where water is, or where forest is, or where urban is, probably the first thing I want to know, does my map underestimate the size of forest, or overestimate the size of forest, or whatever class you have? Straightforward first question. And that's portrayed in the difference in the sizes within that Venn diagram. Oh. So notice back from middle school, you got the Venn diagram. You had this thing called intersection. That's the part that's in both. So here, I've got a name for the intersection. I call it hits. I did not create that name. I didn't create the other three names on here. Those were adopted. I adopted those from other literature that, and I heard other scientists using these terms, but I saw them in a book by meteorologists. Other professions have other names for these four words, but let me cover the four words. Hits is the intersection. Misses is presence in the reference, but absence in your map. False alarms, your map is saying the category is here, but you look and it's not. And correct rejections, both in the reference and in the map, it's absence. In other literature, these will be, let's see, false negatives, true positives, false positives, and true negatives. You'll probably be familiar with those terms. Every time I hear those terms, I need to stop for 10 seconds and figure out. And I see some smiling faces. You've had the same experience. That's been the number one response I've seen from audience members when I explain it. They've had the same experience. It's like, why do you have to have this combinations of these true and negative? So I found these names. Once I start using these names, my thought processes became a lot clearer. Okay, so nearly all of the mathematics that I've derived come from this diagram. I was at a presentation in Mexico, and this scientist was mapping a rare crop species. And he came up, and at the beginning of his presentation, he said his map was 93% correct. And then he started giving some additional metrics. And so I naturally started to try to envision the Venn diagram. After a little while, I realized his Venn diagram of 93% correct looked like that. What's 92 of those 93 percentage points of correctness are the correct rejections, the absence. Okay, so it's like, oh, now I understand if he would have presented the results in the form of a Venn diagram. So, but the Venn diagram is helpful, but it's also helpful to report the size of those four numbers of the misses, hits, false alarms, and correct rejections. So if he presented that, well, I can see here that, let's see, the misses are 5, the hits are 1, the false alarms are 2. If he would have told me that, then I would have known that the true size is 6, because the 5 plus the 1 is 6. Misses and hits, that's the true size, that's the reference size. And 1 plus the false alarms, that's the map size. Okay? So the true size is 6, the map size is 3. The errors are 5 plus 2, 7. So he has 7 percentage points of error. I always like to think in terms of the difference. He told me that the maps are 93% agreement. Don't tell me the agreement. Tell me why, tell me the difference is, you think, okay, come on, kid. If you know the agreement, then you know the difference. It's just different sides of the same coin. But if you start constantly thinking in terms of difference, it will change your life. Because if you're looking at doing error assessment, I like to use the term error assessment rather than accuracy assessment. If you do error assessment, if you understand the errors, then it can help you improve. But to just focus on what you're getting correct, if you get it correct, the natural question is, why did we get it correct? Well, because that's what you were trying to do. A more interesting question is, when you're trying to get it correct, why did you get it wrong? If you know why you got it wrong, then it can help you improve your algorithm. Okay, so he's got, let's see, 7% error, and I'm going to break that error into 2 parts. He's underestimated the quantity by 3 because the reference size is 6 and the map size is 3. And so he's underestimated by 3, and so 3 of that 7 is due to the fact he's got the wrong quantity. Yet his red circle is too small. And then he's got another type of error. He doesn't have the red circle directly on top of the blue one. Okay, so he's got some allocation error. He can correct the allocation error by taking that red and sort of pushing it on top of the blue. And if he does that, if he changes the location of the red circle, he can eliminate the allocation error. The only way to eliminate the quantity error is to increase the size of the red circle. But he's focused on percent correct. Well, if he wants to maximize percent correct, I have some advice. Just predict nothing. You just eliminate the red circle, and most of that red circle is false alarms. If you want to maximize percent correct, just map 0, and you're going to have a higher percent correct. So that's the danger in selecting a metric to try to maximize when you haven't thought deeply about that particular metric, and you haven't thought deeply about the quantity, the particular metric that you want to maximize. Okay, because I don't know. Well, you can tell me. Would you be happier with a map that looks like that, or a map that says the crop does not exist? Well, but there's other ways you could have mapped this. What about this one? Is that a better map? Well, he's made a circle larger, and that just makes more false alarms. But let's think about this. What is the ultimate goal? If his ultimate goal is to estimate the quantity, meaning estimate the size, he's got it perfect. So if you look here, the misses are 5, the hits are 1, false alarms are 5. So the true size is 6, and the map size is also 6. So he has a total error of 10, but the quantity error is 0. He's making no errors in terms of the quantity, but he's not putting the crop, he's not allocating it perfectly in space. Okay? And then that could be one possible option to map this, or think about this one. What about a map like that? Well, gosh, he's got the red right on top of the blue, But let's take a look. Oh, so now there's 0 misses. There's 0 misses, 6 hits, 3 false alarms. So the true size is 6, right? No matter how he maps it, the true size is always 6. But now the map size is 9. Total error is 3, but now he's overestimating the quantity. But he's allocated it as good as he can possibly do. So now the question is, well, which map is the best? It depends what you want. It depends what your goal is. And so you must align your metric with your particular goal. And if you just use metrics because that's what people in your profession do, or that's what my advisor told me, or that's what I see in the literature, you might be making a very big mistake. And like I said, if you're maximizing percent correct, you're going to map 0 of the problem. Here, if you're trying to accurately get the quantity, then that's the best thing. So I presented all of these in terms of a Venn diagram, but you will not see Venn diagrams in research articles, at least certainly not in the form of a circle. If you look closely and use your imagination, you will see rectangular Venn diagrams. So I'm going to take that Venn diagram, rather than circles, I'm going to have rectangles. Venn diagram. Okay, we have a set at the top and a set on the left. Same thing. You will not see that in journal articles. What will you see? You will see that. Okay? That table. Familiar table. It's about in half of the journal articles in remote sensing I read. Okay, next time you see this table, think Venn diagram. Okay, here's one set of the presence of X. Here's another set of the presence of Y. You've got your misses, hits, false alarms, and correct rejections. Okay, and so what this graphic shows is we also have the data up here. Each of you could think of, well, I'm a raster GIS guy, and so I tend to think in terms of pixels. So what we have here are 10 pixels, but for each pixel you have both an X and a Y, and both X and Y are binary. Red is P for presence, and A is yellow. A is for absence. So if Y is presence and X, the diagnosis, is presence, then we get a hit. If the truth is absence and the diagnosis is presence, then we get a false alarm. Then we have another false alarm. Then we have 3 presence and truth, absence and diagnosis. Those are the 3 misses. And then we've got 4 correct rejections. In an Excel, so I've designed an Excel file that comes with the book. You can type in your square matrix, and it makes a graphic like this, where I love stacked bars, but this particular stacked bar, I think here's the presence in X, here's the presence in Y, the intersection is hits, and so, but for these misses, notice there's more misses than there are false alarms. And if misses are larger than false alarms, then that means you have some quantity disagreement. And if for the allocation disagreement, we can pair up the misses with the false alarms, and those pairs make allocation disagreement. Okay. If you go onto Wikipedia at this website, you will find this table. This table has 4 bits of information. You go on Wikipedia, you will find 20 various indices that are a function of those 4 numbers. Why do we need 20? We have 4 bits of information, and each one of those 20 takes 4 bits of information and reduces it to 1. And with that 1 bit of information, you cannot go and reproduce those 4 bits of information. And the first question is, well, how do you decide which to choose? Well, my advice is, wait, why do we need to choose? It might be a bad idea to choose, because if you choose one of these 20, you're going to take 4 helpful bits of information that are necessary to understand the Venn diagram and give your reader 1 number where your reader cannot reproduce that Venn diagram. My advice is just tell your audience the 4 bits of information. If they want to compute their favorite metric, they can. But I think it's more helpful to actually just give the sizes of the hits, misses, false alarms, and maybe correct rejections, and then interpret that in terms of your practical research question. I find that much more helpful than giving kappa, R squared, kappa, F1, you name it, intersection over union, Matthews correlation coefficient. There's been an enormous literature searching for the best of these metrics. All the metrics are faulty because they don't give you the raw information. So I've been thinking about that table for about 20 years on an almost daily basis. And I realized the temptation is to think that here are the 4 bits of information, and then they add up to these outer totals. But I realized the last few years, it's much more helpful to think about, to read this table from the outside in. Yeah, the table has 4 bits of information, but those 4 bits don't necessarily have to be these. When you're going to communicate your research to me, the first thing I want to know is how many observations do you have in total? Okay, where is that? Right there. Okay, so that would be your total sample size, or that would be the size of your spatial extent. So the first thing you do as a scientist, you decide, what are you going to study? How many observations? And then the next thing I want to know is, in truth, how many of those 10 have presence in the truth? And there's a word for that, that's abundance. So notice this 4 has to be a subset of that 10. So now we have 2 bits of information. With those 2 bits of information, I can fill in that. Next thing I want to know is, what's the size that is on your map? That's that bit of information right there. And that's in the mapping, that's how the map maker, that's one of the decisions the map maker makes. And so with that bit of information in the 10, I can figure out the 7. And then I know all of these marginal totals. I just need 1 more bit of information, and it's like playing a mathematical crossword puzzle. If I just know the hits, then I can figure out everything else. Okay. So I find it much more helpful to think in terms of that. And that helps me think about another mathematical procedure called the total operating characteristic. How many of you have ever heard of a more popular procedure called the relative operating characteristic? Rock curves. Okay, that is the most common response I've seen in Brazil, okay? Which is why I added the next slide. I think you will find the next slide extremely helpful. When I first learned about this procedure, it changed my life, because I said, this is exactly what I've been looking for. And the importance of this is, in many cases, your, I shouldn't be touching it. I wonder if I messed up something there. Here we go. In many cases, your x, it derives from an index. Now, maybe your x comes from a machine learning algorithm, and the output of that machine learning algorithm, for every pixel, it might give some number on the continuum between 0 and 1. And the temptation is to call that a probability, just because it's on the continuum between 0 and 1. But it's not necessarily a probability. But because it has various values, you can rank them. You can rank them from high to low. And so what you tend to do is to rank them from high to low, and then have a threshold where you say, okay, the highest ones I'm going to call presence, and everything I'm going to call absence. And then compare it to the presence or absence in the truth. And why? And just think of that it's a tremendous loss of information. But the motivation to do that is maybe you don't know any way to compare a continuous variable to a binary variable. But the total operating characteristic is a way to do exactly that. So on the next slide, the y is not going to change, but the x, I'm going to convert the x to the underlying information, which is an index. So there we go. So it could be that the underlying information is a number, and if it's a number, you can rank it. And I put these in order from high to low. And so I could go through here and take a particular threshold value, and if it's at or above that threshold, call it presence. If it's below, call it absence. And there's lots of ways I could select that threshold. And that threshold is a pretty important decision. For one thing, that threshold is going to dictate my quantity. And then how these are ordered, how your index is ordered with respect to these is going to influence the allocation errors. So I could start off saying, well, I'm going to be very rigorous in my threshold. I'm going to select a threshold of 95. Because if you think of these as maybe your level of certainty that it's presence. So I'm going to diagnose it as presence only if I'm absolutely certain, only if it's greater than 95. Well, if you select a threshold of 95, that means you're going to predict everywhere absence. And then you're going to get this one wrong, but you're going to get those two correct. You're going to get those four correct. Okay? If you predict everywhere absence, you're never going to make a false alarm. You'll never get a hit. Oh. Then you could go along, you could lower the threshold to 90. If you have a threshold at 90, you diagnose one presence and you get a hit. You could lower the threshold to 65. If you do that, then you have 2 pixels of diagnosed presence and you get one hit and one, let's see, absence here, you diagnose presence there, and one false alarm. And you could continue along the sequence, lowering that threshold. For the people at home, let's see, lowering that threshold, and at every threshold, you generate a table like this. So you're going to have as many tables as you have thresholds. That's going to be a nightmare to sort through all these tables. It'd be better to have all of these tables summarized in one graphic that shows the implications of the decision about the threshold. And that's exactly what the total operating characteristic does. Okay, so same data here, same table there, but on the right-hand side, here is the graphic of the total operating characteristic. On the total operating characteristic shows all 4 bits of information at every threshold. On axis here, here's the 10. This 10 is that 10. Okay, that's the total size. Up at the top of the vertical axis, this 4 is that 4, okay, which is the abundance. It has to be less than or equal to 10. Then I said I want to know this bit of information. This bit of information here, the presence of x, that is the coordinate along here. That hits plus false alarms. Hits plus false alarms, that's the presence of x. And then I needed one more bit of information to fill in the entire table. If I know hits, well, hits is the coordinate along this axis. And so with those 4 bits of information, I can fill in the entire table for each threshold. So each threshold generates one of these red triangles. So I'm going to start out diagnosing 0 presence. So if I diagnose 0 presence, my diagnosed presence of x is 0. If I diagnose 0 presence, I've got to have 0 hits. Then I'm going to diagnose my first hit at 90. And yeah, I get a hit. So the diagnosis increases by 1, and the hits increase by 1. Then I lower the threshold to 65. The diagnosis for x increases by 1, but I do not increase the hits. I generate a false alarm. I lower to 50, I generate another false alarm. I lower the threshold to 45, I generate a hit. And so this curve will always either go flat to the right or up parallel to this left band. If all of the highest index values are on the presence, meaning if you would have a perfect ranking, the top curve would go up here and across the top. And up here, well, it doesn't. But at every point on here, the distance between the marker and here is hits. Between the marker and the upper bound is misses. Between the marker and the left bound is false alarms. And between the marker and the right bound is correct judgment. So in one graphic, you can see the implications of your decision on where to select that threshold. And so people will say, well, then which threshold should we select? And, they say, which threshold is best? Oh, that word best just gets my blood boiling, because I always have the same response. What do you mean by best? And then that turns out to can be a difficult question. Okay, but the profession has lots of habits of what they call best, but they don't have my habit. My habit is that you should define best according to your particular research question, which means there should be no universal definition of best. You need to customize your metric for your research question. So that sounds almost obvious, but that doesn't mean it's easy. Let me give you an example from diagnosing COVID. If you're an administrator in the health ministry and you need to manage COVID in a country, and you're going to make diagnostic tests available to the population, the producer of that test needs to select a threshold. Okay? Well, how do you want to select the threshold? In my way of thinking, you think about the disagreement. You have 2 types of disagreement. You have false alarms and misses. Each of those 2 types of disagreement comes with a cost. What's the cost of a false alarm? Well, a false alarm is that a person is healthy, but their test says they have COVID. Well, that's terrible. That means they need to isolate. That means it's really inconvenient. They're going to be separating themselves from their family. Oh, what a terrible cost. Think of the cost of a miss. Someone has COVID and you've just told them they do not have COVID. That person is walking around spreading it to everyone else. So the cost of a miss is much higher than the cost of a false alarm. And so you need to think about that of where you select the particular threshold. Okay, so I find this, and many of my colleagues find this total operating characteristic extremely helpful. I've worked with a brilliant student, Zhen Liu. We have a publication here, and he has created free software, and this is brilliant software, best software in the world for chalk curves. And you can get that, and he's very engaged. If you have a question about it, he'll respond quickly. He's just starting now a doctoral program at the University of Maryland. But the next slide is to warn you what you will see in the literature or in other software. You will see something called the relative operating characteristic. People will refer to this as rock curves. And what I don't like about the relative operating characteristic is the complicated mathematics. I'm a mathematician. I did my bachelor's degree in math. I love math. But complicated math can get confusing. Most of the metrics in my book rely on addition, subtraction, sometimes multiplication, but then I get nervous with complicated math like division. What do I don't like about division? Division takes two numbers, a numerator and a denominator, and converts them into one number. And if you have that one number, you cannot reproduce those two numbers from that single number. And so what we have on all of these axes are sizes that come directly from here. On the relative operating characteristic, these have ratios. These are ratios between 0 and 1. This is false alarms divided by false alarms plus correct rejections. These are hits divided by hits plus misses. And you'll see in the literature, ooh, we have a name for that. That's sensitivity, and that's 1 minus specificity. And I don't got enough things to remember, especially words that start with the same letter and have the same number of syllables. Just complicated. So I would just, you'll see this in the literature, rock curves. You just need to know there's an easier way to think about them, and those are chalk curves. But that's not probably the most popular metrics you'll see in the literature. In the remote sensing literature, you will see a metric called kappa. And kappa has quite a long story. I've investigated it as far as I could go back more than 100 years. Many people have reinvented kappa. I thought that I did when I was a doctoral student and presented that in my first job interview, and the committee said, well, no, this is a standard metric in remote sensing. And so I said, well, why did I go and think I invented that? Well, I did invent it from first principles. And I invented it because when I was a master's student in statistics, they brainwashed me. Every statistical exercise they had us do was it started out that we were assuming that the data came from a random sample, and all of the statistical hypothesis tests that we were doing were asking whether or not the pattern in the data could be explained due to randomness. And so I had that way of thinking in my mind. And that's why initially, early in my career, I thought this kappa was a pretty good idea. But the more time I spent thinking about it, I realized it's an awful idea. And so I wrote a paper with Marco Melonis, who is originally from Peru, and now he's a professor in the United States. And I was pretty convinced in my feelings. And Marcos, I said, Marcos, we're going to call it death to kappa. And Marcos is like, Gil, don't you think that's a little harsh? I mean, why not call it, well, like rethinking metrics of agreement? And I'm like, no, Marcos, death to kappa. I am convinced. And Marcos now tells me, yes, Gil, that was the right decision because that got attention. And so it's become a popular paper, and I made the following slide to illustrate this problem with this kappa index. So for those of you who have not worked with kappa, kappa is an index between 0 and 1. Oh, even it's an index, there's a problem right there. It has a numerator and a denominator, and I'm only going to tell you the ratio. But it's an index between 0 and 1 if it's 1, and it's to compare two categorical variables of the same set of categories. If the kappa is 1, it means your x and y match perfectly with all the categories. If a kappa is equal to 0, it means that the agreement between your x and y is equal to the agreement that you would expect if your variable had been randomly reallocated. Why is that even an interesting question? When I'm making a map, I'm never sitting there, should I use the satellite information that humans have spent millions of dollars to produce, to put satellites in space to get images? Or should I make my map random? Random construction is never the alternative way that you would have made the map. So why is it even an interesting question to have in a metric? Let me illustrate some of the issues with kappa. Got a question for you. Let's say this is your reference, this is your best available information, perhaps created by the visual interpretation of the maps. And you get a satellite image, and there's two classifiers that you could use. There's the classifier in an algorithm that you've used traditionally, and that algorithm has this as an output map. And then there's some other algorithm that this is the output map. So there's a question for you. Which of these two comparison maps is more similar to the reference map? I will give you 5 seconds to think about this. How many people are going to go for comparison map number 1? For the people outside, I see no hands up here, but I know there's probably a few of you out there on video land that are having your hands up. Whenever I ask this question, usually there's one person. How many go for this one? Okay, it's you. And how many people just don't care? Some people have no hands up. It seems obvious to me, but we gotta get mathematical about this. Okay, I try to think as superficially as possible. Minimum thought, okay, is the goal here. Right? Because if you're giving minimum thought, that you should stop at the first most obvious thing. Okay? Let's do proportion correct. Okay, for those of you who selected comparison 2, proportion correct agrees with you. 14 out of 16 agree, and only 2 out of 16 agree for comparison 1. But what does kappa say? Kappa says, well, hold on. You might have got some of these correct due to chance. So kappa is going to say, we're going to compare what you got to if you took your map and rearranged these randomly. And then that's going to be your baseline. So think about that. Kappa is, as a baseline, it's rearranging these after you have selected the quantity. So kappa, look, this quantity is perfect. You might have done a lot of work to get that. this quantity here is terrible, right? You got 15 reds here. You only got one red there. Kappa's going to say, I don't care about the quantity. I'm not going to reward you for getting it right, and I'm not going to punish you for getting it wrong. But however you specify the quantity, I'm going to consider how well you allocated compared to if you would have allocated randomly. And look, here, well, you've only got one green and one green there. So if you would have allocated this randomly, you have a 1 out of 16 chance of getting it right. And look, you got it wrong. Here, you only got one red, you have a 1 out of 15 chance of allocating it correctly. And you did. Wow, that's pretty good. So, what does Kappa say? Kappa selects map number 1. Really? This is the metric. This is the most popular metric for accuracy assessment in remote sensing. It's remarkable. How did we get to this point? My approach is that there's multiple problems with this. First of all, it's focusing on the agreement. Focus on the disagreement. So I look at these and I say, what's the reason for the disagreement? Well, we have 14 pixels of disagreement. Why? Because you got the wrong quantity. You've got too much green and not enough red. Yeah, you put your one red in the correct place. Okay, so that means you have 0 allocation disagreement. So all of the disagreement is quantity disagreement. What about here? Well, holy smokes, you got 15 red there and 15 red there. You got the quantity perfect. But, you have an allocation here. If you swap the position of these two, you've corrected both of the errors. So you have 2 pixels of disagreement and they're both allocation disagreement. So focus on the disagreement, take the total disagreement, separate it into quantity and allocation. I go to a lot of scientific conferences. I love going to poster sessions. And because you can see what people have on their posters and talk to them. So I walk through the aisles and that poster has Kappa on it. I stop and have a conversation. And I ask a truly sincere question. Why did you use Kappa? So I truly want to know. And it's remarkable. Scientists, they really give me directly honest answers. Here are some of their most popular answers. Well, that's what people in my profession do. My advisor told me to use Kappa. The software computes Kappa. People expect Kappa. Kappa measures accuracy. Well, not quite. And Wikipedia has 20 other metrics that measure accuracy. Why Kappa? Kappa accounts for random agreement. Well, that's partially true, but not really. It's only random allocation agreement, but Kappa doesn't punish you for getting the wrong quantity, and it doesn't reward you for getting the right quantity. I need to publish a paper to graduate, and the journal's reviewers and editors insist I include Kappa, even after I cite literature that describes the flaws of Kappa. I got this just last week from a biomass scientist. Yeah, I think he probably made the right decision to surrender and give in. You need to graduate. Right? You need a job to continue to do good science. But once you have a job, it's your responsibility to do what you can to help improve the science. You'd think I'd feel good about having so many citations in this journal article, but every night ResearchGate sends me a publication that has one of my articles cited. Frequently they cite the Death to Kappa paper. I'm like, oh great, let's see what they said about the Death to Kappa paper. I go into the methods section and it says, to compute accuracy, we use Kappa. And they cite the paper entitled Death to Kappa. Was I being too subtle and polite in the title? I know people don't even read some of the journal articles that they cite, but that's why we put it in the title. You don't have to read the article. And so there's many problems in the profession, and many of them are social problems among scientists. Do I blame the scientists? Well, we're all under various types of pressure. I remember being, a young author. There's so many things to learn. What did I do? I trusted the senior people. I went to a university because I trusted the professors. But the professors are humans too. They make mistakes. The most important thing to do is if you've discovered that the profession's going in the wrong direction, you got to do something about it. So, please, and so that's why I'm so passionate about some of these ideas. When I ask people why they've used kappa, it's remarkable. I've never gotten the answer because kappa answers our research question. Never have I gotten that response. Yeah, I'm beating up on kappa, but kappa's not the worst. P-values are even worse. Okay, people say, here's my p-value. But I'm like, but you have data for your entire spatial extent for all time points. You're not sampling. So hypothesis tests are irrelevant. You have the entire population. So p-values are irrelevant. I'm like, well, we want to know if the patterns are different than random. And it's like you're studying land change. Humans don't go out and randomly change the landscape. It takes a lot of effort to change the landscape. You might not understand the patterns, and so some people use the word random to say things that they don't understand. But landscapes do not change randomly. It doesn't seem we should be measuring patterns versus randomness. And people say, well, I want to know if my results are significant. I go, significant. There's a key word. Use the word significant if and only if your p-value is less than the alpha level. Right? And if you don't know exactly what those are, don't use the word significant. This is the advice I got from my advisor, who's a statistician. It's a problem in language because in typical language, people will use the word significant to mean other things, like large. But in science, if you want to describe, if your concept you want to communicate is large, use the word large. If you want to say that it's important, use the word important. But things can be significant. You can have small p-values. They can be significant without being large or important. Okay, I talked about that comparison to randomness is frequently unimportant. To drive this point home, well, we talked about COVID a bit. Let's talk more about doctors. You go into your doctor. Doctor makes a diagnosis of you. You say, well, doc, I want to know how good your diagnoses are. Are you better than random? And if your doctor is that going to make you feel better? If your doctor diagnoses as good as random, that means your doctor has learned zero in medical school. Probably even before your doctor went to medical school, she could diagnose better than random, just from living on planet Earth. Okay, what's more important is how is your doctor wrong when your doctor's wrong? And that's a completely different question. It's very possible to have a diagnosis or a remote sensing classification be substantially better than random, but also substantially worse than perfect? And so the relevant question is, how much less than perfect? Okay, so overall, my message is focus on the disagreement, focus on the difference, because that's where the errors are the things that will allow you to learn, and all those same ideas apply then also to analyzing temporal change. I've been talking mostly about a binary variable, because these relate directly to categorical variables, but some of the same concepts rely to continuous variables or interval variables. Focus on the difference. Here's a question, quiz time. What's the difference between 3 and 1? Well, when I hit second grade, we got into subtraction. And 3 minus 1 gives you 2. I see even for continuous variables, people presenting indices of agreement between x and y for a continuous variable. Look at this question. What's the agreement between 3 and 1? What are you talking about? That question makes no sense. But there are indices of agreement for continuous variables. Just bizarre. Okay, so I said these same concepts apply to analyzing change. So here is what I will do to reconnect the board. And here's what this trip to Brazil has inspired. Drawing more Venn diagrams with rectangular sets. So the blue set is the reference presence at time t minus 1. We're talking about a time interval t, from t minus 1 to t. We're going to analyze change with this Venn diagram. The blue is the presence of the class at the initial time. The green is the presence of the class at the subsequent time. So if it's in both, it's stable presence. Maybe if it's the forest category, 4 is persistent. Here it exists at the initial time, but not at the final time. So that's a loss. Here it exists at the final time, but not the initial time. That's a gain. And then here's stable absence. So you can think of that as the reference change. And Mathiomas is they're making a time series. Why a time series? Because they want to analyze change. So we need same concepts will help with this. So that might be the reference change, what's happening on the ground, but then we need to know what the maps are saying. So here, maybe this is how the maps portray change in terms of the maps, where the red is the presence at the initial time, and the yellow is the presence at the subsequent time. And if it's in the intersection, it's stable presence. So now the question is, well, how do we overlay the reference information with the map information? And what I came up with just this morning was the next graphic. That's a direct overlay of those 2 previous Venn diagrams. So this, we now have 16 possible combinations. That's getting me a little nervous. My brain can't handle that. I'm trying to figure out what to ignore. But I know if I'm analyzing change, it'd be helpful if our reports gave me the hits, the misses, hits, and false alarms for gain, for loss, and persistence. Those would be the most helpful metrics rather than some summary. But if you see the Mathiomas presentation, what are they constantly telling me about the accuracy of their maps? They're telling me percent correct. Percent correct is not giving me any of this information about how to understand how well the maps portray change. So I'm working on this with my students. I promise to come back next year with software for a time series. And if I do not keep my promise, I will submit this figure to a museum of modern art Change gears. But as I've been thinking about this, here is something for you to think about. Look, it's possible to underestimate the size at both time points, overestimate the gross gain, the gross loss, and the gross gain, and perfectly estimate the net change. So we really need to think about exactly what we're measuring. You know, if the goal of Mount Biomas is to estimate the net change, well, then that's what we should measure. But we need to realize that these other metrics, if we worry about them, that we might be measuring the wrong thing. Okay, so we need to be clear for each metric that has each for each concept. Okay, I've been just a few more slides. Let's get directly to the application. We haven't seen enough raster maps from Mount Biomas. Look at the first page of Mount Biomas. We see the map and we see this graphic. When I see this graphic, I think, well, that's showing me exclusively the quantity difference. Okay? We have time, and each line is a category. We see the forest is decreasing, agriculture is increasing. That's telling me only about the quantity. Is that the most important first thing to know? Well, I think maybe, yeah. I think it was a wise decision. But we need to realize there's much more to the story than only the change in quantity. So I've been working with my students. I have some brilliant students in my course, GIS and map comparison, and they wrote code to look at each time interval and look at the change during each time interval. Is an allocation change. So look at these bars. They're more than half allocation change, meaning they're less than half quantity change. And so that means that previous figure, it was telling less than half the story. Because most of the story is that we're having simultaneous gains and losses of the same category on the landscape within each time. We have results also for Pampa. We say the same thing. There's more allocation change than there is net change. My students have software, they've dug deeper to get the exact categories that are exchanging with each other. So in the Pampa, we have agriculture exchanging with grassland. So that means on some places on the landscape, agriculture converts to grassland, while on other places, grassland is converted to agriculture within the same year. We have graphics that show which particular categories are responsible for the net loss. And in Pampa, it's mostly grassland. And if there is one category is having a net loss, at least one other category is going to be having a net gain. And so in that gaining category is agriculture in Pampa. There is also a component that I showed here earlier. That top yellow component is called shift. Shift occurs when you have a category that loses to one category but gains from a different category. So here, grassland loses to one category but gains from a different category. So grassland is involved in what we known as a shift. Okay, this year, I'm the special editor of a special issue of the journal Land. If you have a publication that would be relevant to that, using GIS and land change, please consider submitting it. Here is the website that you or your students can go to get these videos that I mentioned. Here, this is the link to my book. Maybe you can contact your librarian and have your library get the book. And again, to wrap up, to summarize here are the main points. I hope I shared with you how I developed over time my philosophy to focus on the difference rather than on the agreement. The difference is where the learning is. Just remember that Venn diagram. And probably if you cannot explain the metrics in very simple terms, the metric might be a really bad idea. You know, I have a class where I've tried to explain concepts over the years, and those concepts that I found were difficult to explain, after years of thinking about the concepts, I realized they were difficult to explain because they didn't make any sense. It took me a while to realize it. Okay, please use the resources, and also if you know of some students who would make wonderful doctoral students for this next NASA grant, please send them my way. Over to you.
Thank you, everyone.
Very much.
Was great. I think we have some time for questions, right?
I have plenty of energy.
So, anyone have questions?
Yes.
Yes, I have one question. First of all, thank you for your presentation. Amazing. I have a problem with this arrangement matrix, but before the arrangement matrix, because I think that the fragmentation of one class is more important. It is important as how the class is represented with the arrangement matrix. How we can measure this fragmentation in one class.
Okay, and I assume maybe the people, is the microphone coming from here? Also, so I'll repeat the question. So the question concerned that in some cases, the major research question concerns the fragmentation of the class, which is a characteristic that change matrix does not capture. Okay, that matrix is just, it has the 4 numbers. And so from the matrix, you can get the gross gain and the gross loss, but that matrix is based on a pixel by pixel overlay that entirely ignores the spatial arrangement of which pixels are near other pixels. Okay, so if you're concerned about the spatial arrangement, then you need metrics for that. And I have something for you, or I hope I'll have something even better for you next year, as long as Ian Zhang and I are continue our great teamwork. So there are, well, the thing I like about your question is that you realize what pattern is important to you, and you're interested in measuring that pattern. So there is plenty of software that will measure the spatial patterns. Have you used FragStats? Have you heard of that? Oh, okay, so FragStats is one software, and there's other software that specifically measures the spatial pattern. And for example, the number of patches, right? You could have a time series, and at each time point, you might have a particular number of patches. But I have a warning for you that you can find software that for a single time point, it computes the number of patches. But that will allow you to, through time, to make a graph of the net decrease or net increase. But the net decrease or increase derives from gross gains and gross losses. So you're going to be in the exact same position that was on, you're going to be stuck on the first page of Mount Biomas. You can say for a particular category, the number of patches is either increasing or decreasing. But this graphic will tell you nothing about the gross gain or the gross loss. And so my student and I are working on some ideas that I think are going to be really change the profession. So you can think of if there's two ways that you can have a gross increase in number of patches. You can have a patch appear from nothing, or you can have a larger patch split, and both of those will increase the number of patches. There's two ways that you can have a gross decrease in number of patches. You can have a patch just entirely disappear, entirely lose, or you can have two patches merge, and both of those will cause a gross decrease in number of patches. So on a single landscape, you can have all four happening: appearance, disappearance, splitting, and merging. So stick with us. Ian's working hard, and we hope to have software for you by next year. Yes?
Okay. What can clarify resolution spatial images? Will we go to these objective-oriented?
Yes.
And it is sometimes using cover, I always felt like I don't want to look at the pixel because the pixel doesn't tell me what I want. I wanted to count view research.
Yes. Yeah.
And I wanted to hear a little bit about what directions you go.
Yeah. And so I'll repeat it, and I don't know if they heard on here. So the question concerned how to measure maps that are created by object-based image classification, where your classifier makes clusters of pixels, and then you want to do an analysis or some comparison where the unit of analysis are those patches rather than the individual pixels. So I have a paper for you. I'm the second author. The first author is Su Ye. The last name is Y-E. And Su Ye is brilliant. And we also, these are two of my doctoral students, Rahul Rakshit. We reviewed 200 papers that used object-based image analysis and for comparison, because we were interested in metrics of accuracy assessment and comparison using object-based image analysis. And many papers claimed that they had mathematical methods to have a straightforward comparison of these patches, but I don't see any, in my mind, I don't see any clear way of comparing two maps that take the same landscape, maybe two different algorithms. The two algorithms make different patches, right? You can take one piece of software, and depending upon how you adjust the parameters, you can have big patches or small patches, and then you might want to compare them. I've seen some bizarre papers claiming that they're comparing them, and they'll say they will pair up that, a patch in one map with a patch in another map. But then if they pair them up, I think you could do that if they had the same number of patches. But typically your maps are going to have different number of patches. So to pair them up, I just think makes no sense. And so I encourage you to read that paper, but I've worked with both of those students to think about this, and I don't know of any very clear, straightforward way to compare two maps. Oh, it was a few years ago now. Yeah. But if you write to me, I can send. Oh, in fact, even better yet, I have listed all my publications on my website here. And you can go there, and if you click on that publication, it automatically sends me an email message, and I can send you the PDF, and it's legal. If I post it to my website, it's not legal, but we can do this legal. It's always convenient. Yes?
I had a more natural question.
validation points is compared if you are right or wrong.
Yeah.
How many validation points you need to be?
Yes. Okay. So that's so the question is, well, when you go to do the error assessment for the maps, typically you generate the reference data by having people look at the raw imagery and make an assessment of what they see visually. And that's very time consuming. So what people typically do is to have some sampling method. So the question was, how many points should we sample? And well, that's an excellent question, and there are standard ways to compute that. Well, there's standard ways to compute that in if you think about it in a very simple way. But there are other larger things that you need to think about when designing that sample. And one is that you need to think seriously about having a stratified sampling design, because it's possible to waste a lot of time asking the people collecting the reference data to collect the reference data in places where they're not helping, they're not generating helpful information. So it's best to have a stratified design where you make some strata where you think you are most uncertain, and then other places where you are certain, and then put most of your observations in the places where you are uncertain, and fewer observations in the places where you are certain. Because the logic is, if you're going to invest the effort to get more information, you want that information to be helpful. And so you look for where you're most ignorant. And then it's important to know in each stratum how many observations you have and the size of the stratum. And with that information, you can take your raw information from your validation and then convert it to an unbiased estimate. And I mention that because I think many people in the field miss that. They just have their team collect the raw information, get their confusion matrix, and analyze the confusion matrix. But that raw information was collected from a stratified design where some strata are sampled more intensively than others. So that's a major problem in the profession. So make sure you do that. If you want a quick, clear, easy answer, put 100 observations in each stratum. Okay? If you put at least 30 observations in each stratum, the concepts of the central limit theorem will kick in, and you'll be able to have legitimate computations of your confidence intervals. Okay? If you have 100 observations in each stratum, I'm certain the concept of the central limit theorem will kick in. So you're going to be safe. Oh, yeah.
Not for classification. It's for validation, right?
Yeah. Well, right. So MAPI almost has tens of thousands. Okay, so what happens in statistics when your sample size is that large? You're going to be able to measure with precision things that are extremely small. And so you can, and then if you find some results that are significant, you need to realize that, say, significant means specifically that the p-value is less than the alpha level. And if you need to revisit that, or if that's not clear in your mind, then don't use that word significant. But the important thing to know is, if you make lots and lots of observations Your confidence intervals are going to be very narrow. That means you're going to be able to detect very small differences. So you might be able to detect a difference, a significant difference that's so small that it's unimportant. So an enormous sample size will allow you to measure things that are so small they might be unimportant. So that's why these concepts need to be very clear in your mind about exactly what the objective is. But I think when I've heard presentations on the map-Biomass sampling design, I've thought, well, that sounded pretty intelligent to me. They do have stratification where they know in remote sensing it's most uncertain on the steep slopes. And so the strata they have more samples on the steep slopes. Brilliant. Good idea. The other very, very good thing that they've done is when they select a point to get this validation information, they look at every single year for that point. Brilliant. And that's crucial because it's only with that information that you're going to be able to do the analysis that I've been working on that says I'll promise to have you for next year. We need to know the hits, misses, false alarms for the gain of each category and hits, misses, false alarms for the loss of each category. And the only way to get that information is for each sampling point to know the entire history through time. Does that answer your question?
So I can ask you that.
Yep.
So you know very well the business model of McDonald's, right? We are concerned about dynamics, change protection. And when you talk about the allocation problem, it's a huge problem. Not a problem, but it's a characteristic of McDonald's. Next, I'm thinking now, can we have higher accuracy in a temporal dimension, but a lower accuracy in a spatial dimension? I don't know if
Okay.
myself here, because I think with the allocation, if I try to map where the things change, and it's important because we're trying to look where the things are changing, to calculate greenhouse gases effects and all this stuff, but without, I don't know if I can use the word accurate, but it's not right. But if I look at the temporal dimension, it's okay, even with the allocation errors, I'm getting the right amount of change, right? But what is better for McDonald's case, like to have a better accuracy in the temporal dimension or better accuracy in the spatial dimension? It doesn't matter.
Okay, so the question concerns, should map-Biomass aim for high spatial accuracy in the temporal dimension or the spatial dimension? Okay, so let me translate that question to my way of thinking. I like to think in terms of disagreement. So should map-Biomass be more concerned about errors through time or space? And especially because a goal of map-Biomass is to estimate change. But I guess my response to that question is that I think map-Biomass has several goals. And we're a large team. We have many questions. And so each question requires data of a particular quality. And so I think it's almost obvious you want a metric that's aligned with your research question, but it's not exactly clear which metric is going to address which research question. But as far here's like the graphic in the temporal dimension. Okay, this is showing change through time, but this is all about quantity. So if the goal is to show this with as little error as possible, then the main goal is to worry about the quantity error. And But even when you think of this, this is showing both the size and that if it has a net gain or a net loss. Well, maybe you don't even care about the size. Maybe you just want to know how much is the net loss or the net gain. So here's the thing that I've really been obsessing about is this sentence. This is something I've just started thinking about the last few months. It's okay. Let's say let's say the truth is some decreasing size of forest. But let's say that at both time points you are underestimating the size of forest. So that means if this is the truth, your maps are showing this. Well, those two lines, they show the exact same size of loss, of net loss. But that's the net loss. But you could be overestimating the gross gain by the same size that you're overestimating the gross loss. But if you do that, it's possible to estimate the net change perfectly. So you really need to think carefully about exactly what you're measuring. Because you might say, oh my God, my maps are terrible. We're overestimating the gross loss. But if the goal is to estimate the net change, you might be estimating the net change perfectly. And how well you estimate these two might be very different than estimating the size at a particular time point. So again, the message is think about exactly what your research question is, and then design a metric for that research question. But it's a simple idea, but that doesn't mean that it's going to be simple to implement. So for example, if your research question concerns threats to biodiversity, then you need to start thinking about patches and patch dynamics. You need to start thinking about not just how much forest there is at every time point, but whether or not you're losing forest at the same time you're gaining forest, right? You can, like the persistence of, if you have all persistence of forest, that's probably pretty good for biodiversity. But if you have large losses of forest and the same size as large gain of forest, the size of forest can be constant, but it can be damaging for biodiversity because, they don't have the places to remain. Does that answer your question?
Yeah, yes, sir. When I ask it because don't show where the losses are occurring,
right,
the gains are occurring in the temporal dimension. It's not easy, but I can affirm that it's consistent, right, with the data of the RPC. Comparing the collections, the materials, it's mostly consistent, right? Thinking about forest regrown, this kind of stuff, and it's sending a lot of wrong things. Depending on the allocation, because I'm a little confused about the effects of the allocation in the map itself.
Yeah. Yeah. Well, so when I think about the allocation errors, I think if you have for a single class, if you have false alarms in one region and misses in another region, and if your false alarms are the same size as your misses, then you pair those up. And if you can make them all pair up, then all of your disagreement is allocation disagreement, and you would have no quantity disagreement. So if the size for a single class, if the size of your false alarms is the same size as your misses, you're estimating the quantity perfectly. You have zero quantity disagreement. And so I think it's important to map those and to look at them. Sometimes just looking at the map, you can you can see patterns that, some metrics would not measure. But you're going to be in the position that your maps, or in the map biomass collection, we don't see misses and false alarms. We see gains and losses. Why? Because the map biomass data doesn't show the validation data. And even if it did, it wouldn't be particularly helpful because those are samples from individual points. And the data sets are so enormous, how do you even begin to look at that? But how you begin to look at that is exactly during this method that I've been working on with my students. So what we plan to do for next year, while we're trying to develop software now, that it shows through the time series how many misses and false alarms you'll have for gain and loss, through the time series. So that's why it's important to have that validation data for all those points that you have the presence or the category at through the entire time series. Okay, very good. Well, thanks for watching online, everyone. GIS TV. Look, the crowd, they're doing the wave. Oh no!
I hope there's no questions.
No, it doesn't have. I checked.
Maybe someone.
Oh, there is one.
There's one.
Just now.
There is one. Don't go away
here
yet.
and here.
Yeah. Is that how much do you think that raster? How much do you think that raster classified from biomass can lose information from each category? Wait, let me read this again. How much do you think that raster classified from map biomass can lose information from each category? I do not understand the question.
Você pode perder informação dentro de classificação.
And that's Erica. Are you still there? Can you elaborate? Maybe why I signed off before Erica could see. Okay. Well, I guess my one response is that I was about to say we know that the data are not perfect, but I'm not even certain if I can be certain about that statement. Because if they were perfect, how would we know? We would need to compare it to perfect information. But if you look at all that validation information that enumerators had training to produce, you get trained experts who look at the same point and disagree. So if your best available information is from experts who cannot agree, how can you say that your maps are wrong? Right? You can say whether your maps or not agree with experts who cannot agree among themselves, but so I have lots of concerns about even trying to make the data conform with that validation reference data, because I consider that validation reference data, that's just another way to do a remote sensing classification. And who's to say that that's any more accurate? Because, especially those humans that are looking at that point, well, I want to know exactly what they're seeing. Do you just give them the visual image of the raw imagery? And maybe, the human eye can only see so many wavelengths. but the classifier might be able to be using wavelengths that humans cannot see. So what makes us think about that the visual assessment is more accurate than the remotely sensed classification? You know, and so I'm going through the exact same procedure with my students. We're doing a visual assessment to collect reference data in a coastal wetland. And, you know, it's easier to do the automated classification, but to come up with the sampling design and to train the people to do the visual assessment, oh my God, it's a nightmare. I mean, this is a coastal region. We have tides coming in and out twice a day. You know, sometimes, you know, we're trying to classify if it's water or not. The two easiest things the easiest class to distinguish. Well, what's water? Is that much water? Water? Or does it have to be that much? Or if we had a storm, we have 5 years, 2 years apart. So 5 years over a decade. Why? Because we are studying climate change. And so we want to detect sea level rise. And so we have these 5 time points, generally from the same month of the year. But if there was a big storm the day before the plane went over, there's going to be this much water, but that's not sea level rise. That was a storm. That was last week's storm. Or if we don't know what phase the tide is in, it's uninterpretable. You know, if from the first year we're looking at low tide and the last year we're looking at high tide, you know, it looks like sea level rise is going to wipe us out. But if the first year is high tide and last year's low tide, it looks like the sea's retreating. So it's, we have shadows that the shadow, in some years, the shadows are on the east because it was an afternoon image. On other years, the shadows are on the west because it was a morning image. And, you know, these shadows, they're just dark and the water looks dark. And so the shadow is right on the place where we have a big mound right next to the water. And then the images are misregistered. So I don't think we should I think we should certainly not be thinking that our goal is to make all the map biomass data conform to that visual assessment. And maybe unless we understand the visual assessment better. And we should not be judging the quality of the data based on that comparison. How do I judge the quality of the data? Can you access it? Is it documented? Can you find the definitions of the classes? I know lots of databases. They fail at those criteria, you know? And so it's the more fundamental administrative things, I think, is much more important when we think about data quality than accuracy. I see another question. I'm not sure, but I think the question was something like this. How much information can the classified map biomass image lose in each category? Yeah, that's the same words I understood before that I read before that I didn't understand previously. How much information can the classified map biomass image lose? Does anyone else? Is there a translation from Portuguese that?
I don't understand the same.
Okay.
But, it's a difficult question. It's basically asking if we know how much of the information we are not mapping or we are losing it. It's related to everything we're talking about.
Yeah, it's related to everything.
Yeah.
Right, and I mean, and how would we know? I mean, in order to know how much less than perfect the maps are, we would need to know perfection. And if we knew perfection, we wouldn't have to make the maps. So, the sampling to get that reference data, that's an effort to compare to perfection. But once you know how those reference data are generated, then you realize, I don't want that to be our definition of perfection. So I guess it's a great mystery. We'll never know. I mean, we do the best we can, and we try to give some guidance for other people to how to interpret the data. But I think the presentation of metrics that are as easy as possible to understand are crucial. I know, one thing I love about Not Beyond Mouse is we're trying our best to communicate to the public, and we certainly don't want to do that with Kappa. And we shouldn't even be communicating to other scientists with Kappa. And I don't think we should necessarily be communicating to other scientists about percent correct, right? Because percent correct can really lead you to have extremely biased results, right? Just like in the case that I started out with, if you're dealing with a rare category, you can maximize your percent correct by underestimating the size. Or if you have a large category, you can maximize percent correct by overestimating the size. And so, I mean, even when you're running your classifier, to maximize percent correct might be a bad idea. And when I was presenting in Belém, there was a student, she said every time she ran a classification, she was trying to maximize kappa. And so she'd end up with a map like, that the comparison one map, if she's maximizing kappa. So you got to be really, really careful. And what's dangerous is there are really bad habits that are deeply ingrained in the profession. And so you got to be careful even to trust the peer-reviewed literature. And so my recommendation is, if you do not understand it clearly, then don't do it. Because I've even had mistakes in my profession where I've said, well, all these other people sound like they know what they're doing. I'm gonna trust them. And then years later, I thought, well, that was a bad decision on my part. So I guess beware of things that are difficult to understand, because it might not be your lack of understanding. It might be that the concepts just don't make any sense. Those things exist in the profession.
I think it would be very nice if we had a workshop or something like this, like a short workshop where you can like hands-on.
Yeah.
And for usual classification of assessment.
Yeah.
I mean, most of you are professors also.
Yeah.
Replicate this kind of problems. And it would be nice if we can look at something online. 1 hour, 2 hours, just short.
Hopefully, Professor Pontus will be here more and more.
Yeah.
If you can go back, even from US, I think it would be nice to arrange something like this.
Okay, so it's Patricia, right?
Yes.
So Patricia said that it'd be nice to have a workshop. In fact, I do have a workshop that it can range anywhere from half a day to 3 days. And I have a video of all 3 days in my website of the videos. But it's helpful to have some some hands-on computer helpful workshops. Yeah, I've given them during COVID via Taiwan to 200 people. So it's possible, but like I said, I plan on coming back to, especially Bahia for hopefully several years. I'd be happy to give a workshop. Even when last month when I was in Porto Alegre, we made plans to have a workshop next year. And so they said maybe in Argentina. Said where it's less expensive. They said. So yeah, that's very possible. But one thing, well, with my book, I gave the link to my book. I can send you an Excel file where you just type in the cross tabulation matrix, the confusion matrix, and it computes these helpful metrics.
So that's it.
Okay, that's it.
On behalf of the University of Miami, thank you for patience and our knowledge that you give to us today. And that's it. Hope you come back.
Okay, I hope I come back too. Thank you very much for your hospitality. Okay, now say goodbye again out there in TV land.